Hello, chemistry students. Professor Sean McMahon here. This is chapter 4, Atoms and Elements, and we are on the last topic, lecture 5, which is discussing periodic trends. In this particular lecture, we'll talk about things that we notice using the periodic table to determine whether or not something's going to increase in its size as far as an atom goes, whether it's going to be harder to remove an electron from an atom, whether it has more metallic character. And all of these trends can be determined using the periodic law and what we understand of elements. So we're going to have to use our previous lectures where we talked about the atomic structure, but most importantly, the most recent lecture on electron arrangement. It's all about the electrons. When you think about chemistry, it's movement of electrons, forming bonds, and breaking bonds. When we have bonds forming and breaking, we have chemical changes, chemical reactions. These chemical reactions sometimes also manifest in releasing energy in the form of heat or light. So we talked a little bit about light. We use light to help us understand the location of electrons and how they can be excited and drop down to lower energy levels. And when they do that, they can emit light. We also use electron arrangement to understand the number of valence electrons. Now that is really critical in determining bonding patterns as we move forward in the course, and also physical and chemical properties of the elements. So in this particular lecture, we're going to continue using the electron arrangement and valence electrons to help us identify physical characteristics of different elements. I want to also let you know there'll be, if you need, there are additional videos that I will have for the course for electron configurations, some of the exceptions when I have ions, what to do. But for the bulk of the course, I've covered most of it, but I do have a few additional videos for you to watch if you need to further your understanding for electron configurations, orbital diagrams, and just atomic theory in general. Okay, for periodic trends, what we need to do is the periodic trends are talking about certain chemical properties, and we're going to use the electron configuration, but more importantly than the electron configuration, we're going to look at the valence electrons, because the valence electrons are going to show us a repeating pattern, a trend. That's why we organize a periodic table in these families or groups, okay? So chemical periodicity is the variation in properties of elements based on their position in the periodic table. The periodic table tells us what's going to happen, okay? The electron arrangement helps us understand why. So let's consider 3 trends: atomic size, which usually has to do with the radius, like from, you can think of the nucleus to the outermost energy level, which I talked about as the outer, shell of electrons, or the period. Ionization energy, which is basically the amount of energy required to remove an electron, and metallic character. Now, there are additional trends. One trend, electronegativity, we will discuss in a future chapter when we talk about shapes of molecules and the bonding. And that has to do with the ability to pull electrons in a shared pair towards itself, for an atom's ability to do that. Another trend that we are not discussing is what's called electron affinity. The amount of energy that's released from an atom when it gains an electron and becomes more stable, trying to seek out a noble gas configuration. But for now, let's talk about atomic radius. So whenever people think of atoms, they think that they're spherical in shape. So remember, the bulk of the atom is empty space, right? So you have this dense nucleus, electrons outside. Well, where are the electrons located? Well, we just talked about energy levels, and then within energy levels, there are sublevels. And those sublevels have orbitals, and those shapes, right, are regions of space that these electrons will occupy 90% of the time. So really, when we think about atoms being spherical, we're basically lining up all of the orbitals in each sublevel and overlapping them, because there's going to be overlap. You got your 1s orbital, the 2s is going to go on top of that. It's just further away. And then the 3s and so on. So we overlap all these orbitals, and it comes to roughly a spherical shape. But again, the majority of this is just regions that electrons can occupy, but the majority is empty space. And you get, again, I hate to use a solar system example, but it's really good. You got the dense nucleus, the sun, and then you have all these planetary bodies around it in these regions of space that we can call orbitals. So as a review for shells and subshells, shells are the layers of the group. So you can think of onions, right? They have layers, and they're groups of electrons around the nucleus. The more shells, the larger the size. So really, the shells, the layers, are those principal energy levels. And we use principal quantum number n, right? So the first shell or energy level is in the first period, first row. Then you have the second, then you have the third. So more shells, they're stacking on top, and they're getting further and further away from the nucleus. And that's why the further you go down on the periodic table, the more periods, the further the electrons are in that shell, and the more potential energy they have. Because remember, in earlier lectures, chemical energy stored in bonds is based on electron positions. So the further the electron is from the nucleus, the more energy it has. So the subshells, the S, the P, the D, the F, are inside those energy levels, those shells, and they don't really add any thickness because they're just overlapping in the available spaces because they have different shapes, okay? So for when we talk about atomic radius, we're going to go across periods. So that's left to right. We're adding electrons, but we're also adding protons. So we have to remember that. And this is going to help us understand all the trends. So let's start with atomic radius. The obvious one based on this diagram, and just conceptually, the one that's really easy, as I go down the periodic table, right, I'm increasing the periods or the shells, the energy levels, right? So I have my first shell, then the second, then the third. So as I go down and I have more and more shells or layers, it makes sense that the atom's getting bigger, okay? What's a little trickier for students is as I go left to right, across the period, I'm not adding an energy level, right? But as I go left to right, I'm in the same shell. I might be in different subshells, but it's within the same shell, just squeezing in different locations and regions, but I'm increasing the number of protons, right? Because my atomic number as I go left to right increases. So even though I'm in the same energy level, my atomic number goes up. So it's actually called in other courses, in the nucleus, that's where you have your protons. So I'm increasing my nuclear charge as I have more protons in the nucleus. So if I have more positive charges, I can pull in that shell of electrons closer because I have a greater pull on them. So that causes, as we see as we go left to right, kind of a contraction, and we see the atoms getting smaller. Now, there's always exceptions. I'll have an additional video for exceptions, not just for the electron configurations, but periodic trends as well. But right now, I want to focus on the main portion for this course. So going down a family is easy. More shells, bigger. Going across is trickier. I'm in the same shell, so the relative size is the same, but now I have more protons pulling on that, so it causes kind of a contraction. So it decreases. So I always tell students, think of it this way, right? As I go down, it increases. as I go left to right, it decreases. So drawing little arrows helps me. You can even, put, helium right here just so you know where you're going. So for sample exercise 10, which element is bigger? Well, let's use a periodic table, right? And if I'm comparing calcium with beryllium, they're both in the same group, 2A. Or sorry, yeah, 2A. So they have the same number of valence electrons, 2, right? So they're both the S2 sublevel. But really what I'm focusing on is they're the same distance left to right, but calcium is in the 4th energy level, where beryllium is only 2. So calcium has to have 2 additional shells. So which one's bigger? Calcium. So when I look at sulfur and aluminum, right? So here's sulfur, here's aluminum. Now this is a little different. They're in the same shell, principal energy level 3, but who has more protons pulling? Aluminum has 13, sulfur has 16. So 16 protons pulling on that shell has a greater pull than the 13. So the sulfur contracts more. So that means aluminum is bigger. What about chlorine and potassium? So here's chlorine, here's potassium. Well, chlorine's further on the right, and it's up higher. So it has fewer shells and more protons for that shell. So the potassium is bigger because the chlorine's getting pulled in better, right? It has fewer shells, so it's smaller. And left to right, it has a lot of protons for that particular shell. Last but not least, if we were to compare beryllium and nitrogen, same energy level. Nitrogen has more protons. I could look at the atomic number. So beryllium's not going to pull that shell as well. So beryllium's a bigger atom. So that's kind of atomic radius. What's another trend? Ionization energy, the amount of energy required to remove an electron. So the closer the electron is to the nucleus, the harder it is to pull away the electron. So obviously smaller atoms, it's harder to remove their electrons because their valence shell is closer to the nucleus. As the atom gets big, it's easier to take away the electrons. So think of it as like magnets. When they're really close, it's hard to pull them apart. As they get further away, it's easier to pull them apart, right? So there's an attractive force between the protons in the nucleus and the electrons. But as the electrons get further and further away, yeah, they have more energy, but it's almost easier to take them away. So the basic trend, what do we notice? Ionization energy decrease. It's easier to remove electrons as I go down. Whoops. As I go down, and it's harder to remove electrons as I go left to right. Now, there are some dips. I'll talk about those exceptions in an additional video that I'll add for the outline of the course. But for the focus, I want to think, well, why as I go down is it easier to remove electrons? Well, remember, if I go down, there's more and more shells. There's more shells. The outer shell is further from the nucleus. It's easier to remove. So the ionization energy decreases. It's easier to remove it. If I go left to right, now I'm in the same shell, but there's more protons pulling on that shell, so there's a contraction. So now, compared to the nucleus, the shell's closer. It's harder to remove those electrons, so it increases. So which one of these elements is it going to be harder, right? Larger ionization energy. Which one is it going to be harder to remove an electron? From lithium or potassium? Well, they both have one valence electron. It's in the S sub level, so it's an S1 position. But lithium is a smaller atom. It's only got 2 energy levels, right? So 1, 2. It's closer to the nucleus than potassium, which has 4. 1, 2, 3, 4. So it's going to be easier to remove an electron from potassium because lithium's closer and has a larger ionization energy. So what about between potassium and bromine? Well, they're in the same shell, but bromine's further to the right. It has more protons for that shell compared to potassium. We haven't talked about this yet, but just to let you know, nonmetals, they don't like losing electrons. Okay, they do not like having their electrons removed because they're so close to the noble gases and having that p sublevel filled. In fact, nonmetals, they're willing to share, but when we talk about ions, nonmetals steal electrons from things that have low ionization energy, and they steal them and form negative charges called anions. Where metals, they're really far on the left. They're far away from getting a noble gas configuration. And it's a lot easier to remove an electron from a metal. In fact, potassium, which is a 4s1, right? Because it's in the 4th energy level in the s block, and that's its valence shell, and I could say argon, right? It actually wants to lose this valence electron because if it loses it, now it's like argon and it's happy. It's easier to lose the 1 electron than gain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It's easier to lose 1 electron than gain 7. But for bromine, it's easier to gain 1 than lose 17. So if potassium and bromine are next to each other, potassium, right, is going to give its valence electron to bromine. And when it loses an electron, it becomes positively charged, which is called a cation. And the bromine, right, it gains that extra electron. Potassium becomes the bromide ion, which is an anion, negatively charged. So typically nonmetals form anions, negative charges, and metals form cations, positive. But that's the future. Okay, you don't have to, right now we're still on atomic structure. You know, I'm getting a little ahead of myself, but it's just to help you understand what's coming. But going back, who's it going to be harder to remove an electron from? Bromine or potassium? Bromine doesn't want to lose an electron, right? It wants to gain it. So it has a really high ionization energy, does not want to lose it. So the bromine has a larger one. Potassium has a low ionization. Basically, you know, the lowest ionization energy, right? Francium. Why? The electron shell's really far and there's not a lot of protons for that shell. So this is the easiest, this has the lowest ionization energy. Who's it hardest to remove an electron? Who has the largest ionization? Helium. Why? It's got a lot of protons for that one little sublevel 1s. So it's really tight and small. Okay, what about between phosphorus and chlorine? Same energy level. Which one has more protons? Which one's closer? You can think about it. Which one's closer to that noble gas for that energy level, right? Which one's closer to argon? Chlorine, larger ionization energy. With the earlier example, they were in the same energy level, but which one was closer to krypton? Bromine, larger ionization energy. That's why this has a really low ionization energy, right? It lets you take its electron because if you take its 1 valence electron, now it's like argon. Because again, it has only one valence electron. Which brings me, when I think of that little staircase separating metals to non-metals, metallic character. How can I determine whether or not something is metallic? Well, a characteristic of metallic character is they want to lose electrons. That's why metals conduct electricity, because electricity is just movement of charge. It's basically electrons being passed through a wire. That's what a voltage is. So who wants to lose electrons? Metals. Why? Because they'd have to gain so many to fill their outer shell. They'd rather lose a few electrons than try to gain a ton. So if we use that criteria for metallic character, the atoms with low ionization energy are more metallic. So metallic character is basically the opposite. So this corner is most metallic. Why? Well, cesium, the electron's really far, and it doesn't have a lot of protons for that energy level. It has that one electron in its valence shell, and I know that because it's in group 1A. So cesium's like, it's too much work to gain all these electrons. Just take it. So it'll lose one electron to be like xenon, right? So this corner is high in metallic character, but low ionization energy. This region is low in metallic character, but has a very high ionization energy. And it all has to do with size. These are really small atoms, so harder to remove electrons, so, right? So that makes them high ionization energy. Not metallic. In fact, we said earlier, on this side, we have non-metals, so they're not metallic. This region, we have huge atoms, so it's really easy to remove electrons, right? And you, as a result, they're very metallic because metals like to lose electrons. So which element is more metallic? Oh, I didn't put the periodic table. I'm sorry. Potassium. Why? It's further down. Between potassium and bromine. Well, bromine's a non-metal. So non-metals aren't metallic. Potassium. Between phosphorus and chlorine. They're both non-metals, but which one's closer to the noble gas and has a higher ionization energy and is smaller? Chlorine's smaller. Oh, oh no, phosphorus, I'm sorry, my bad. Phosphorus is in the third energy level. I believe chlorine's in the, oh, here we go. So I have phosphorus, chlorine. Oh yeah, this is more metallic. Chlorine has a higher ionization energy. It's more of a non-metal, it's closer. So it doesn't want to lose electrons. Phosphorus is closer to the metal, so it's more metallic. It's a bigger atom. It's easier to remove the electrons, so that is right. So now, as your last kind of exercises, now I'll just throw all of these different periodic trends, and using the periodic table, choose which one for each trend. So which one's a larger atom? Lead or polonium? So which one's larger? Lead. Which one's larger? Chlorine or selenium? Well, selenium, it's a whole period below. It's a whole shell further away. Who has higher ionization energy? Which one is it easier or harder, because it's higher, to remove an electron? Is it harder to remove an electron from magnesium or strontium? Well, strontium is further down, which means it has more shells, so that's easier to remove an electron. So the one that's harder has fewer energy levels. That's magnesium, so that has a higher ionization energy. What about between copper? Let me erase these other ones because it's starting to stack up. Between copper and phosphorus. Well, copper is a metal. Phosphorus is a nonmetal and it has fewer shells. So which one's going to hold on to its electrons better, right? Nonmetals, they don't like losing electrons. Metals don't mind. Copper wires. So which one has a higher ionization energy? Which one's harder to remove an electron from? The nonmetal phosphorus. Now we're going to go opposite. Which one's more metallic? Copper or gold, which I think that's the AU. So which one's going to lose electrons easier? Which one's bigger? Solid gold. What about nitrogen or silicon? Nitrogen's smaller, so it's going to hold on its electrons better. Silicon's bigger. It's not going to hold on it as well. So it's going to lose its electrons easier, the silicon than the nitrogen. So if it loses electrons easier, it's more metallic. Right? And you can see it's going closer to right here, right? It's as you go towards that corner, you're more metallic. As you go towards this corner, you're smaller as an atom and higher ionization energy. So that is the last slide, and I'm covered chapter 4, where we talked about atomic structure and the subatomic particles. We know that the protons are positively charged, the neutrons are neutral. The protons and neutron contribute to the mass and are one atomic mass unit. The electrons, we now learned, are not just outside of the nucleus, but they're in specific orbitals in regions of space that have certain energy levels based on their distance to the nucleus. The electrons are negatively charged, so they're attracted to the positive nucleus. So as I go further away, they have more energy, but it's easier to remove them, right? It's easier to remove them, and it makes the atom bigger. Okay. When we're talking about bonding, we're looking at only the valence shell, the outer shell for the elements when we're talking about bonding, and that's what we use the valence electrons for Lewis dot structure. So I hope that helps. Thanks for watching. Let me know if you have any questions, and I'll see you next time. Thanks so much.